Hey, welcome to what will be a series of videos uh, starting with the basics of setup here, which is going to go through some basic terminology and exactly what's happening when your car is on track and rolling. So let's get started here. So this is the way that I look at it. There's four primary keys to a great setup. There's a whole bunch of secondary ones as well that have an effect on your setup, but the primary ones are this: tires. If you don't have the right tires, you're wasting your time. So make sure you've got the right tires before you start messing around with your setup, because if you don't have the right tires, you're not going to go anywhere. The next key thing is the balance. You'll hear race teams and so on talking about balance all the time. So this is a distribution of the weight transfer between the front and the rear of the car. So this is affected by your front and rear roll stiffness and the position of the center of gravity in the fore-aft direction. So where the CG is between the axle lines. The next one is the response, and this is basically the overall stiffness of the chassis, and it's affected by the sprung mass, how much or how heavy the sprung mass is, the roll stiffness, the sprung mass CG height, and the roll center positions. So it's kind of an overall indicator of how stiff the chassis is and how responsive it will be to requests to change direction. The indicator in RC Crew Chief is a term called chassis roll sensitivity. So that term is listed on the suspension properties in the setup tab, which we'll see in a minute. The last important part, and this is probably the most important part, is your tire contact patch. You have to try and maintain as much tire in contact with the racing surface as possible in order to get the maximum grip. So the contact patch is affected by your static camber setting, so what you set your camber to when it's sitting on the bench, and the camber gain, and also the chassis roll sensitivity, because the chassis roll sensitivity affects how much the chassis rolls. So a very stiff chassis will have very little roll, and a very soft chassis will have a lot of roll. So obviously that's going to affect your change in your camber angles. So goal is, as I mentioned, to try and optimize that over as much of the G range as you possibly can. Next, we're going to talk a little bit about tires. There's a couple key things that you need to understand here, but the likelihood of us ever being able to get our hands on tire data is probably non-existent. What I've got here is a graph of an F1 tire. This is not a current one, so nobody needs to get too excited. This is probably 10 or 15 years old. But what this does show you is one set of curves, which gives you the lateral force that the tire will develop, versus the slip angle. The slip angle is the difference between the axis of the tire and the direction the car is going. So if you think of the rear wheels on a normal RC car, usually we run about 3 degrees of toe in. So even if you're going in a straight line, your car is already running 3 degrees of slip angle in the rear. And as you change direction, those slip angles change all over the place. And you can see here the range for this tire's operating range is from 0 to 6. Once you get beyond 6, then the lateral grip starts to fall off. So what we can gather from this graph is we got lateral grip, slip angle, and then each one of these lines here is a line of constant vertical load. So the bottom one, that's the performance with a 400-pound vertical load. That's 600 pounds, 800 pounds, 1,000 pounds. So I've drawn a little red line here which picks up the peaks So you can see here that the peak lateral grip is at different slip angles depending on which load you're dealing with. Now, the other thing on this graph that's really important to understand is the fact that the tire, you can see the distance between these lines is getting smaller and smaller as the load goes up. So if we want to look at a case where, let's look at two cases. Case one will be a low weight transfer case, and case two will be high. So we're transferring a lot of load from the inside of the car to the outside of the car, and the other one we will be transferring a lesser amount. So if we say that for our high load case, we're going to transfer, our outside tire is going to be operating at this peak line here, and our inside tire is going to be operating on the bottom line here. So if we just assume that we're at optimum slip angles and everything's just golden here, the high load transfer case, we would have on the inside tire approximately, let's call that 700 pounds. And on the outside tire, we would have something in the order of 1,300 and let's call it 80 pounds. So our total lateral grip would be the sum of those two numbers, which would give us about 2,080 pounds of available lateral grip. So let's look at our other case where we're just going to say that we're only transferring between 800 and 600 pounds. And in this case, we would have a peak value here of, let's call it 1,240 pounds, and let's call this one 1,020 pounds. So the total of those two is 2,460 pounds. So even though we're developing less total load on our outside tires, the total grip that we have available is greater than this one. This one we had 2,100 pounds plus or minus. This one here we have 2,460. So we got 360 pounds more lateral grip because we kept these numbers close together. So that's an important consideration. You want to try and minimize the lateral load transfer as much as possible, and that's going to allow you to maximize grip. Okay, let's move on. So now we know we want to minimize lateral load transfer. How do we do that? So just looking at the vehicle from an overall standpoint, we can easily calculate what the total lateral load transfer for the car is, and this will just tell us what the total load that we're transferring from the in this case from the inside tire to the outside tire. And that equation is the weight of the vehicle times the lateral acceleration in G's times the height of the center of gravity above ground divided by the width of the track. So that's how simple this is. It's a very simple equation. So if you want to decrease the amount of weight transfer, you want to lower your center of gravity, which is what every race car wants to do. You want to minimize the weight, which every race car wants to do. And you want to get the track width as wide as you possibly can. So in all cases, set your ride height as low as you can. This is more of an on-road thing than an off-road thing. Off-road, you have some other restrictions as far as clearing bumps and landing off jumps and all that sort of stuff. I'm just thinking here from an on-road standpoint. So that is what you want to try and achieve to minimize the lateral load transfer, and that should maximize the grip available from your tires. So knowing the total amount of weight transfer is a good thing, but we really want to know how the weight transfer is distributed between the front and rear. So in order to do that, we got to do a little more work. This involves separating out our sprung and unsprung masses and also determining their CG positions. We also need to know the front and rear roll centers. I'm showing them on here, and the suspension roll stiffness. So if we can separate all this information, calculate our roll stiffness, and and roll centers, then we can start determining how much weight transfer we have going to the front of the car and how much we have going to the rear car. So you can see on our little graphic, we've got our front unsprung mass, our rear unsprung mass. So the unsprung mass is essentially the weight of the wheels and axles and everything that's outboard of where the spring is connected or the shock is connected to the suspension arm. It also contains a portion of the weight of the suspension arm and the shock itself. So we've got all those pieces of information calculated. Then what we need is to connect the rear roll or front roll center and the rear roll center with a line which is called the neutral roll axis. So the neutral roll axis is the theoretical line about which the chassis is rolling. The amount of roll that is induced is a function of the distance of the height of the sprung mass, center of gravity, above the neutral roll axis. So this dimension here from the center of gravity of the sprung mass to the intersection point with the neutral roll axis, that is the rolling moment that is induced in the chassis. Okay, so let's move on. So here's just another view. So I've switched things over now. Instead of just having the overall vehicle, now we're looking at what we've just described here. So we've got our unsprung mass of our wheel times the lateral acceleration, and in this case it's divided by 2 because we've got half of it on each side of the car. And then we have our sprung mass represented here. So we have our height of our sprung mass above the neutral roll axis, and we have the weight of the sprung mass times the lateral acceleration, which is what's inducing the rolling moment. So now we've got all that information together, we can start displaying a bunch of suspension properties. So these are the properties that are listed on the right hand side of the setup tab in RC Crew Chief. So we've got the front and the rear, and our roll center position is defined here. Roll center is measured relative to the ground, so negative means it's below ground level, positive means it's above ground level. The lower the roll center is, the greater the rolling moment is, which we just discussed is the distance from the center of gravity or the neutral roll axis, which connects the front and rear roll centers to the sprung mass center of gravity. The ride stiffness, this is a measure of the vertical stiffness. So if you take your car and you press vertically up and down on it, this is the stiffness that you're feeling. Normally you want to have the rear ride stiffness slightly greater than the front, assuming you have fairly equal weight distribution front to rear, which most of our cars do. The reason being is that that ride stiffness affects the ride frequency, and you always want to have the rear ride frequency higher than the front, because this is going to help the car settle faster after going over a bump, because once the front starts oscillating at its frequency, and the rear is going to oscillate slightly faster, so it's going to catch up to the front and essentially cancel itself out faster. If you have the opposite condition, you can actually get into what would be termed a pitch oscillation, where the car would start pitching forward and backwards. So fairly simple there to keep those numbers in that kind of range. Next, we're looking at the roll stiffness. So the roll stiffness, there's two contributors to that. There's the contribution due to the springs, and there's the contribution due to the anti-roll bars. So those two are provided for you separately here, and the sum of them gives you the total roll stiffness for that end of the car. The next thing we do is we take these total roll stiffness values and we calculate what we call a roll couple. So this is a very simple calculation. It's just the front roll stiffness divided by the total, which would be the sum of the front and the rear roll stiffness, and expressed as a percentage. So if you consider a car that has the center of gravity right in the center between the axle lines, if this number here is less than 50%, that means your front is softer than the rear. You're going to be into a handling tendency that would be towards oversteer. If you're greater than 50%, then you would be in a situation where the front is stiffer than the rear, and you would be looking more for a handling tendency that would be towards understeer. Now the last number here is the chassis roll sensitivity. We talked a bit about this at the beginning. So the chassis roll sensitivity basically tells you how soft or how stiff the chassis is, because essentially what it does is it equates the forces that are trying to roll a chassis to the forces that are resisting it, which is your springs and your anti-roll bars, and comes up with a number that tells you how much the chassis will roll per G acceleration value. So in this case, if we look at a 1G acceleration, the chassis would roll approximately 1 degree. 2 Gs, it would roll a little more than 2 Gs, or 2 degrees. So it's an indication of the overall stiffness of the chassis. The smaller this number gets, the less it rolls. The stiffer the chassis is, the more responsive it is. Higher, softer, more roll, easier to drive. So this number is a really good indicator, and you should look at it and pay attention to it as you're making setup changes to your car. Okay, last but by no means least, we're going to talk about camber. So our static camber is measured at ride height, and this is our static camber here. So we have a fairly typical minus 2 degrees of static camber. And once the chassis starts to roll, this whole situation changes, and you generally on the outside tire are going to start losing camber. So you want to try and maintain that normally. Sometimes you don't, but sometimes you want to try and maintain that. So to do that, you use a term called camber gain, which is a function of the angle, primarily of the angle and the length of your upper camber link. So how it's measured is in RC Crew Chief is we displace the chassis vertically down. So you can see here I've displaced the chassis by some value y, and then the program calculates what our new camber value is. So in this case, it went to minus 2.8 degrees. So our static camber is minus 2. Our camber gain is minus 2 minus 2.8, or gives us 0.8 degrees of camber gain, because the camber is increased from minus 2 to minus 2.8 for that displacement. So this is a good indication when you're making setup changes. If you want this number to go up or down or whatever, you can just pay attention to it in the setup tab, and you'll see more of this in future episodes. So the best thing I can do here is to show you a little demo. So I'm just going to get out of the slideshow here for a minute, and we're going to go into RC Crew Chief, and I'm just going to do a quick demo here of what camber gain effects are doing to you. So this is the dynamic tab. This is the best way to look at camber effects. So you can see here we've got our suspension. We got some pointers here that show us what our camber's at. Our suspension setup right now, we have minus 1.5 degrees of camber. So let's just animate this. So now you can see here we have bars which show what the total amount of camber change is. So in this case, we just click on this. This is our outside tire. So we're just going to slightly positive, and we'd call that 0. So we're essentially ending up at 0 degrees of camber at the end of our little simulation here, which is going out to 2G's lateral acceleration. So let's say that we wanted to maintain some more camber. We're finding we want more grip, so we want to maintain more camber. So let's change the angle of this upper arm. As I mentioned, this is the camber gain is a function of the length of this arm and the angle of this arm relative to the lower arm. So right now we've got about a 1/4 degree of camber gain. So we're going to go all the way down here. So we've shortened the arm and we've increased the angle significantly. So now we're up at 1 degree of a little over 1 degree of camber gain. So we're going to apply that. Now the graphs have updated, so now you can see we were basically at 0. Now we're at just a little bit less than 1 degree camber at the peak acceleration value of 2G's. So we can just animate this now, and you can see we've also narrowed how much our camber changes because we have a lot more camber gain built into the system now. So we'll talk a lot more about this in future episodes, but that's it for now. So be sure to subscribe to RC Crew Chief channel on YouTube, and you'll get notices as to when new episodes are available. And I'm going to try and get out as many as I can as quickly as I can, but I want to do it properly as well. So you'll see me again soon.